Students, welcome to video session. Let's learn something new today, and let us continue the problems. Yesterday, in the previous session, we have solved around the two problems. Now, in this session, let us solve bit complicated problems and one of the important problems. So the question is like this: a rod of diameter 15 mm and 50 mm long is subjected to tensile load of 25 kilonewton. The modulus of elasticity for steel rod may be taken as 200 kilonewton per mm square. Find stress, strain, and elongation of rod due to applied load. This is the question. Students, let's try to solve this question. Once again, I'll read the question carefully so that I can note it down the given values, given data. A rod of diameter 15 mm. So diameter is 15 mm and 50 mm long. So that is nothing but length is 50 mm. Okay. Is subjected to a tensile load of 25 kilonewton. Tensile load is nothing but P equals to 25 kilonewton. The modulus of elasticity for steel rod may be taken as 200 kilonewton per mm square. This is modulus of elasticity, that is nothing but Young's modulus. Capital E is equals to 200 kilonewton per mm square. Find stress, strain, elongation, stress. I need to find the stress. So F is equals to question mark, strain, E is equals to question mark, then elongation, that is delta L is question mark. Students, we are done with given data. Now, just go through the given data and check whether unit conversion is necessary or not. In case of diameter, there is no need of conversion. In case of length, no. What about load? Yes, we are supposed to go for the conversion because it is in terms of kilonewton, but we need only in terms of Newton. So the value becomes P equals to 25 into 10 power 3 Newton. And in case of Young's modulus, it is 200 kilonewton per mm square. So again, we need to go for the conversion. So the value becomes 200 into 10 power 3 Newton per mm square. In place of kilo, we have to write 10 power 3. Okay, done. So as I said, there are few steps we need to follow. That is area, stress, strain, Young's modulus, lateral strain, and engineering constants. Step by step. First, I'll do with the area. Area is formula A equals to pi by 4 into d square. First check how many unknown values are there. A is unknown. Yes. Pi by 4 is a constant value. What about diameter? A is given. So we have only one unknown value. So we can solve for area. So let's substitute the values. A as it is equal pi by 4 into d is nothing but 15 square. A equals to pi by 4, value of pi by 4 is 0.7853 into 15 square is 225. On calculation, I get the value of A is 176.6925 mm square. Next, we need to find the value of stress. Stress is equals to F is equals to P by A. It is very simple formula. Just go through how many unknowns are there. Do we have the value of F? No, it is unknown. We have one unknown value. What about P? It is known. What about area? We know. So we have only one unknown value. So we can solve for stress. F is equals to P. P is nothing but 25 into 10 power 3 divided by area 176. On calculation, I get F is equals to 141.4887 Newton per mm square. Once I'm done with stress, then I will go to the strain. Strain is nothing but E is equals to delta L by L. Just cross check whether values, how many unknowns are there. What about E, strain? Do we know the value of E? No. That's what we need to find. Okay. What about delta L? Do we know the value of delta L? No. We have, that's what we need to find, right? So we have two unknown values. What about length? Yes, we know the value of length. Here we have two unknown values. If we have two unknown values, then it is very difficult to solve. So that is why I'll skip the strain. Just I'll skip. Then I'll go to the next step. What's the next step? It is Young's modulus. What's the formula? Capital E equals to F by E. Young's modulus is equals to F by E. Just cross check how many unknowns are there. What about the value of capital E? Do we know the value? Yes, we know the value of capital E. What about stress? Yes, we know the value of stress. What about strain? No, we don't know. So that is why we have only one unknown value. Definitely, if we have only one unknown value, then we can solve it. The value is 200 into 10 power 3 is equals to what about F? F is nothing but 141 divided by E is nothing but unknown value, right, as it is. With simple cross multiplication, I get this step. Just I will cross this E to this side and 210 power 3 to the right hand side. With the help of a calculator, I'll get the value of E is equals to 7 into 7.074 into 10 power minus 4. This is the value of strain. And one more thing very important is it doesn't have any kind of units. Okay, okay, done. Students, we are done with Young's modulus. Once we are done with Young's modulus, before going to the next step, just to come back to the previous step where we didn't get the answer. In case of strain, we didn't get the answer. We didn't solve that. So you go back to that strain. So once again, I'll take the formula for strain E is equals to delta L by L. Since we have not got any kind of value for that. So just now cross check whether can it be can we solve it or not. What about what is the value of E small e strain? Do we know that value? No, it is unknown value. Okay, what about delta L? So here it is unknown, but so where is the value of delta L? Again it's an unknown value. What about L? We have 50 mm. So again we know that there are two unknown values, but on clear observation we will come to know that we have only one unknown value, because though we have written E equals to question mark, just previous step we have found the value of E. Just we have found the value of E. So no, it is no more unknown value, it is a known value. So we know the value of E. Delta L is unknown, only unknown, one unknown. What about L? L, we know the value. So we have one unknown value. We can go ahead for solving. Just simply just substitute the values is equals to delta L as it is divided by L. What about the value of L? 50 mm, 50. On cross multiplication, I get 7 into, this is the value on cross multiplication, I get, so this is the delta L. With calculation, I'll get the value of delta L, that is 0.0353 mm. So this is the value of delta L. That's it, right? So he has asked to find the value of stress. This is the value of stress. What about strain? This is the value of strain. This is the delta L. This is the value of delta L. That's it. It's very simple. Students, I hope you understood this question. So I hope you have understood the question, and also you have understood the method how to solve this problem. Okay, done. Now let's move on to the next question, students. The question is like this. It's a very important question. The following data pertains to a tensile test conducted in a lab where D is the diameter, of a specimen 15 mm, length of a specimen is 200 mm, extension under a load of 10 kilonewton is 0.035 mm, load at yield point is 110 kilonewton, maximum load, that is ultimate load, is 190 kilonewton, length of the specimen after the failure is 255 mm, neck diameter, that is final diameter, is 12.25 mm. Okay, this is the question, students. Okay, students, this is the question, and he has asked us to find Young's modulus, yield stress, ultimate stress, percentage elongation, percentage reduction in area, and safe stress, adopting a factor of safety 1.5. So this is a question he has given. Okay, okay, I'll write the given values. So solution. First, let me read the question step by step so that I can note it down the given values. Diameter of the specimen is 15 mm. Diameter of the specimen is nothing but D, small d. D is equals to 15 mm. Length of the specimen is 200 mm. L is equals to 200 mm. Extension under a load of 10 kilonewton is 0.035 mm. Students, it's very careful. You need to be very careful because he has given the two values and two terms. Extension under a load of 10 kilonewton is 0.035 mm. On clear observation, on clear reading, we will come to know that extension is 0.035 mm and the load is 10 kilonewton. Okay, students, if you get confused while reading, if you get confused, which is the load and which is the extension, whether is 0.05, 0.035, is it a load or extension? If you get such confusion, then you are supposed to check the units. Students, as we know, load will be having a units of Newton, right? So already 10 kilonewton, it is a Newton. So definitely this should be a value of a load. Okay. Okay, done. So P is equals to 10 kilonewton and delta L is nothing but 0.035 mm. Next, load at yield point is 110 kilonewton. Students, right now we came across only the load. It is a load. But what he is saying, load at yield point, he is saying that load at a particular point. So we will write, we write P for the load. If I want to write load at yield point, then I need to write it as a Py. P indicates load, Y indicates yield point. This is what I need to write. P nothing but load, Y is nothing but yield point. That means load at yield point is 110 kilonewton. Okay, I think you got this. Maximum load, that is nothing but ultimate load, is 190 kilonewton. Once again, students, load means P. He's asking ultimate means U. U for ultimate. If I write PU, then it becomes ultimate load. So PU is equals to 190 kilonewton. Well, length of the specimen after the failure. After failure, that is nothing but final length, students. Final length. So failure is nothing but breakage. So I will call it as a LB. If I write L, it is a length, initial length. Here I am supposed to write the final length. So that is why I will use the term LB. L is nothing but length, B is nothing but a final. Instead of writing F for final, I'll write it as B because it's a breaking point. LB. LB is nothing but final length. It is, this is 255 mm. And neck diameter, D is nothing but diameter. Neck diameter is also is nothing but final diameter. So what I have taken for final, that is P, breakage, breaking. So I should write DB. Only D is nothing but diameter. What about DB? Final diameter. Okay, very simple. That is 12.25 mm. This is what the given data is. And also what I need to find Young's modulus. And one more thing he has given, factor of safety is 1.5. So factor of safety is 1.5. And he's asked us to find Young's modulus, capital E equals to question mark, then yield stress. You see, stress is nothing but F. Yield stress is nothing but Fy. Ultimate stress. F is nothing but stress. Fu is nothing but ultimate stress. Very simple. Similarly, P is nothing but load. Pu is nothing but ultimate load. P is nothing but load. Py is nothing but yield load. Similarly, F is nothing but stress. Fu is nothing but ultimate stress. Fy is nothing but yield stress. Good. Then he has asked us to find percentage elongation, then percentage reduction in area. So by adopting factor of safety 1.5. Students, after writing the given values, just cross-check whether unit conversion is required or not. In case of P, I need a unit conversion. That is P equals to 10 into 10 power 3 Newton. And also in case of yield load, I need to go for the unit conversion. So, and ultimate load, I need to go for the unit conversion. There's one more thing he has asked us to find, the safe stress. By adopting factor of safety, I need to find the safe stress. That is nothing but F. I need to find the value of a safe stress. Okay, these are the unit conversions I need to do. First, as usual, as our normal method, I'll go with the area. A equals to pi by 4 into d square. Just analyze, is it possible to solve? Do you have the value of diameter D? Yes, it is possible. A is equals to pi by 4 into what's the value of D? 15, 15 square. On proper calculation, A equals to pi by 4 is the value of 0.7853 into 15 square is 225. Then the final answer for area is 176.6925 square. Very simple. After getting the value of area, then it's a time to calculate the value of stress. Stress formula is F equals to P by A. Again, cross check whether do have how many unknowns are there. Do we know the value of F? Do we know the value of F? No, we don't know the value of F. What about P? Yes, we know the value of P. What about A? Yes, just now we have calculated. So it is, we can solve because we have only one unknown. We have write F as it is. And what is the value of P? P is nothing but 10 into 10 power 3. Okay, divided by area. What's the value of area? 176. This is the value of area. On calculation, I get the value F equals to 56.5954 Newton per mm square. This is the answer. After calculating the stress, then I'll go with the strain. Strain is equals to E equals to delta L by L. Just cross check. Can we solve this or not? What about value of strain? Do we know the value of strain? No, we don't know the value of strain. It's unknown. What about delta L? Do we know the value of delta L? Yes, we know the value of delta L is known. What about L? Yes, we know the value of L. Since we have only one unknown, we can go ahead with this formula. So E is equals to, on substitution, E delta L is nothing but 0.035, L is nothing but 200. On some simplification, we get the value of E, that is E equals to 1.75 to 10 power minus 4. This is the value of strain. Okay, students, once I get the value of strain, then I'll go for calculating the Young's modulus. Young's modulus, what's the formula for Young's modulus? E is equals to F by E. Just cross check. Can we solve this formula? How many unknowns are there? Can we solve E? Do we know the value of E? No, it's unknown. What about F? Yes, it is known. What about E? Yes, it is known. So since we have only one unknown, we can solve this formula. So write as it is, E equals to F. Just substitute the values. E equals to 56.594454 divided by E equals to 1.75 to 10 power minus 4. On calculation, I'll get E is equals to 323402.2857 Newton per mm square. This is the value for Young's modulus. Okay, students. Students, right now we have finished with all our steps. After Young's modulus, we are supposed to go for the lateral strain and Young's then engineering constants. But in this question, we are unable to find lateral strain. Okay, it's very simple because in order to find the lateral strain, we need to have change in dimension with other parameters, or else we need to have the Poisson's ratio. We don't have such values, so we will try to find the questions that are asked in the question. We need to find the parameters that are asked in the question. Right now, Young's modulus was asked, so we got the value of Young's modulus. Now we need to calculate Fy, yield stress. Okay, so next. So yield stress, the formula is simple. The formula for stress is F equals to P by A. Students, the formula for stress, what is the formula for stress? F is equals to P by A. This is the formula for stress. This is the formula for stress. F equals to P by A. If I need yield stress, yield is nothing but you need to add Y here. If it is a yield stress, you need to take a load at yield point. Just add Y at F and P. This is the formula. In case if I want to find the yield ultimate load, we know the P by A is the value of stress. If I want to calculate the ultimate stress, just add U in case for F and also for P. That's it. This is the formula. Okay, you just say Fy equals to Py by A. So we know the value of Py and also we know the value of A. Just substitute the values. Just substitute the values. So Fy equals to 110 into 10 power 3 divided by 176.6925. On calculation, I will get Fy equals to this much, 622.5504 Newton per mm square. This is the yield stress. Once again, I need to find ultimate stress. That is, ultimate stress is nothing but Fu. Fu is equals to Pu by A. Simple. Just now I explained how to write a formula for yield stress and ultimate stress. We know the value of ultimate load, and also we know the value of area. Just substitute. Fu is equals to 119 to 10 power 3 divided by 176.6925. On calculation, I'll get the value of Fu ultimate stress, that is 1075.3144 Newton per mm square. Next, I need to find a percentage elongation. Students, there's one more formula for percentage elongation. Just to go through this formula, that is LB minus L divided by L into 100, where LB is nothing but final length, L is nothing but original length, initial length, divided by L is nothing but initial length. So we know the final length, initial length also values of. So on substitution, it becomes 225 is nothing but final length, 200 is nothing but initial length, divided by 200 into 100. On calculation, I'll get 27.5% is the percentage elongation. That means after applying such load, 27.5% length is increased. Okay. Next step is percentage reduction in area. The formula is says in area. So always remember, students, if it is elongation, then it is in terms of length. If it is reduction in area, then it is in terms of area. He has mentioned clearly that is reduction in area. That is A minus AB by A into 100. A is nothing but original area. AB is nothing but area at the time of breakage, area at the time of final failure, or else area at the time of failure. That is the AB. So just substitute the values. So before substituting the values, we know the value of A, but what about AB? We don't know the value of AB. That's what we are supposed to find. The formula is simple. AB equals to pi by 4 into dB square. Very simple, students, because the value of area, what's the formula for area? A is equals to pi by 4 into d square. This is the original area. If I need final area, just add b to the area and also b to the diameter. Simple. This becomes the area for final area. Okay, that's what I did here. On substitution, we know the values of dB also. Final substitution, pi by 4 into dB is nothing but 12.25 square. dB is nothing but 12.25. Since it has a square, I have put a square. So on a final calculation, I'll get the value AB equals to 177.8440 mm square. This is the final answer for AB. Once I get the value of AB, I need to substitute back in the formula for reduction in area. On substitution, so the formula becomes reduction area equals to 176.69, where is the original area in the previous slide. And AB is nothing but just now we have calculated divided by original area into 100. So the answer is 33.3%. That means 33.3% of area has reduced on application of this kind of load. The one more thing we need to find is with the help of a factor of safety. With the help of factor of safety, I need to find safe stress. I need to find a safe stress. How to find a safe stress? Very simple. First, I'll write the factor of safety. Factor of safety is equals to FOS equals to FY by F. Students, very careful. You need to be very careful because we have two formulas for factor of safety. One is for ductile, one is for brittle. Since this material is a ductile material, how do you say it is a ductile material? Because he has given the yield stress. He has given the yield stress. That is why we need to take ductile. Okay. In order to avoid that confusion, very simple. In the question, if in the question he has given yield stress and ultimate stress, if he has given both the values, yield stress and ultimate stress, you are supposed to take yield stress as the reference. If he has given only the ultimate stress, then you are supposed to take ultimate stress as itself a reference. In this question, he has given yield stress and also ultimate stress. So I should take yield stress as a reference. Simple. Substitute the values. Factor of safety is nothing but 1.5 is equal to yield stress. Just now we have calculated 622.5504 divided by F. On cross multiplication, I'll get the value of F is 415.0336. So this is the answer for safe stress. It's very important, students. Once again, I'll explain you for factor of safety. For factor of safety, we have two formulas. One formula is, that's what I have written this formula, and one more formula is FOS is equals to FU divided by F. This is FU divided by F. So you need to be very careful which formula to be used. What I am saying is, if you have two values, that is Fy and Fu, then you are supposed to use Fy. If you have only Fu, then you are supposed to take Fu. There is no other alternative. If you have both, then you are supposed to take Fy. Okay, so this is the formula. On substitution, I'll get the value of F. This is the solution for this question. Students, I hope you have understood this question. In the next class, I'll deal with another set of problems related to engineering constants. Okay.